Hello community! Today I want to talk to you about why SBERT sentence embedding is not BERT sentence vector embedding. To make it absolutely clear, I'm going to show you the difference between the SBERT model versus the BERT sentence vector model. So here we go. If you have not seen my video on BERT vector and BERT sentence vector, a very short summary in 1 minute. What is BERT? BERT is based on a transformer, but it just uses the encoder of the transformer, and it is an encoder stack. As you can see here on the left side, we have 12 encoder stacked on top of each other, and given an input, it's coming from the bottom, and we have a sentence, of course. Sentence is, how are you? And you know, since it's BERT, we have a specific word piece tokenization. We have a classification token at the very beginning of each and every sentence. This is the CLS token. Then we have an embedding layer where all our words are compared or translated to a numerical representation in our vocabulary. And then we are entering the first encoder layer. And we run through 12 encoder layers, and the output is a contextualized embedding of this sentence. Now, contextualize is so important because if you compare it to word to vec, we have a static embedding. And the beauty of BERT is that it works at first bidirectional, and we have a mechanism called self-attention. Now here we have a look at this encoder. And if you're not familiar, just to tell you, in each of these blue layers, what's called encoder, we have two sublayers. Now the first is a multi-head self-attention mechanism. Maybe you remember this beautiful research topic, attention is all you need. And the second, within those blue layer, is a simple position-wise fully connected feed-forward network. And then you have this thing stacked 12 times, 24 times, if you use with the BERT large model. And each encoder has an output, and those are those little yellow boxes here you can see given each word. So for each word we get from each encoder layer an output. And as you can see here now, we have, given that we have a BERT base model, the output is a 768-dimensional vector representation for each word and for each specific or special token like our classification token. And now we are in front of the big question, which vectors of those 12 700-dimensional vectors we take for a single word? Let's say our word is how, the first word in our sentence. And you might say, hey, of course, I take the last encoder layer, the output of this last encoder layer. This is my 768-dimensional vector representation of the word embedding. And it is not a static word embedding, but a contextualized embedding because we have the self-attention mechanism in BERT. Somebody else might say, well, in my models it performs better if I take the last 4 layers. And remember, either you can concatenate those vectors to create a 3000 plus dimensional vector space, no problem at all. Or you say, for my 4 768-dimensional vectors, I calculate the mean value of it, and this is my vector representation of this word, of this single word. So you can see, this is just a convention. This is some empirical knowledge how to create a word vector. Now let's increase the complexity a little bit. BERT sentence vector. BERT originally was invented, let's say, for the word vector. The sentence vector came later and was not the main topic of BERT. But they thought about, hey, if I have now this stacked BERT, the stacked encoder layer with 12 encoder, which output of which encoder level should I take if I want to encode a sentence of all the words in a sentence? And they came up with, hey, what are the special tokens that are not really words, because words have a specific contextualized embedding within the semantic of a sentence, but what non-words do I have encoded with self-attention? And well, of course, the first position was the classification token, also a specific token by word piece, since we have a tokenization level of word piece with BERT. And now you have to ask, okay, if I go for the CLS token, which of the 12 or 24 layers, the output of which layer do I take as the specific sentence vector representation? Now, if you go for a commercial product, you will see that it is not the last layer, but interesting, it is the second to last output of the encoder layer of the stack, which they take as a vector representation for the whole sentence. Because of self-attention, this CLS token, this classification token, think about it as a lighthouse. It is so tall and bright that it sees all the different words in the sentence. So it can look down all the words in the sentence, and because of self-attention, it is also integrated completely into semantic contextualized embeddings. So, one solution might be the second to last output of the encoder layer in a 768-dimensional vector representation. Or again, you take all of the 12 output layers and you calculate the mean, or you concatenate them, or you normalize them, or whatever you want to do. So you see, it is not a law of nature how to do this, but it is rather an empirical finding. Somebody tested this 10 times, 100 times, and found for a particular configuration, it should be the second to last layer. So keep in mind, however you do this word embedding or sentence embedding on BERT, you have a variety of solutions. A very short interrupt. Just to tell you about the heads on BERT, please do not confuse it with the self-attention head in a transformer block. What do I mean? Here you can see BERT. BERT is the pre-training of a deep bidirectional transformer for language understanding. And you have here all the different transformer blocks in BERT. Beautiful. Now, BERT consists of two training steps. At first, you have the pre-training. You know this. BERT for pre-training as a model is trained on mask language model, where you mask certain words and you have to find the word embedding for this particular word and next sentence prediction. So you have a sentence A, this is here in whatever kind of red this is, and a sentence B, this is kind of lila. And the model, the BERT for pre-training model is pre-trained with two heads on top of BERTs, and you have a mask language modeling head and a next sentence prediction head. And then after, and yes, of course, what I want to show you also is the BERT model, the transformer outputting raw hidden states without any specific head on top. This is called a BERT, the pure BERT model with no head on top of it. And now after you have done the pre-training step with the classical BERT, you start to fine-tune it. And the beauty is, of course, that the pre-trained BERT model, you take the BERT model with all the different layers and all the different weights and everything that it learned, pre-trained it, and now you additionally fine-tune it with one or more additional heads or output layers on top to create state-of-the-art models for specific tasks. And you can see here on the right side, we have BERT for mask language modeling, BERT for next sentence prediction, BERT for sequence classification, BERT for multiple choice, BERT for token classification, BERT for question answering. You choose your specific BERT model with the specific head on top of BERT. This is then fine-tuned, and then you have a fine-tuned BERT model, a task-specific BERT model. And now, I know that some of you tell me, hey, BERT is trained on next sentence prediction in a training set. Yeah, but have a look at this. I have here a sentence A in the training data set. Sentence A is, today is a sunny day. And a sentence B that follows right next after sentence A is, I will go for a swim. Now, BERT is trained now on the next sentence prediction task, and it will learn if it sees sentence A, it expects sentence B to follow. But keep in mind, with SBERT, and I will show you in a second, we will train sentences on their semantic similarity. And now I ask you, given sentence A and B from BERT, guess the semantic similarity, let's say in the unit of the cosine similarity of those vectors in the embedded space. How close would you call these two sentences based on a semantic similarity? So you can see here clearly what is the difference on BERT, the next sentence prediction, what sentence comes after a sentence. So if you want a logical structure or a question and answer, you have a question, sentence A. Hey, how is the weather today? Question mark. Sentence B, the weather is fine. So here you understand clearly that you have the next sentence prediction in BERT that is useful. But if you want to guess the semantic similarity of sentences, maybe have a look at SBERT. And now to SBERT, the newer model. Now SBERT, we have to understand a very basic concept, a Siamese neural network. What is it? Now this is a special class of neural network that contains two identical networks. And I mean really identical. They have the same network configuration, the same parameter in each layer, the same layers, and they have the same weights. And even if you have backpropagation through both of them, the parameters are updated, updating is mirrored across both networks. So they are really Siamese, they are twins, identical 1-1 twins. And we need them simply to find a similarity of inputs. And we compare in the feature vectors, and let me show you a very simple visualization of this. So here on the left side we have two packages that are input to two neural networks that have the same network configuration, the same parameters and the same weights. And then we have a loss function. And this is it more or less. You optimize the loss function, you minimize the error, we have backpropagation, and the network learns perfectly. Now, since the weight are to be identical for both convolutional neural networks, for example, we use just one model and feed it two images, one after the other. After that, we calculate the loss value using both images, backpropagate, and this saves us a lot of memory. And talking about convolutional neural networks, yes, I really mean CNNs. Here you have Learnet 5. You really see here you have a completely neural network, a black box, where you have a flow of weights between your two CNN models that are identical, and you compute the loss function and everything else. And now you guess, if we talk about SBERT, that our neural network, our Siamese neural network, are not going to be convolutional neural network, but based on transformers, a BERT model. So we will have two BERT models. Let's have a look at this. SBERT. SBERT is Sentence-BERT, and it calculates sentence embedding using a Siamese BERT network. So let's have a visualization. We have as an input a sentence 1 and a sentence 2. We have sentence pairs. And we have, in our black box of neural network, we have now a BERT model. We have a BERT model with 12 stacked encoders. And each encoder has an output for each and every word. And then the output of our BERT model goes into a pooling layer. And the pooling layer you see here in orange has only one job: to achieve a fixed size sentence embedding. This is it. But of course you can achieve this, as I showed you, by choosing different output layers, concatenate them, or just focus on a specific layer, whatever. So here I show you 3 options that were implemented in SBERT, and you can choose in code in SBERT. You can focus also on the CLS token, beautiful. You can calculate the mean value of all output layers, or you can choose the maximum over time for all outputs. Whatever you choose, the pooling layer will result in a vector A for the sentence 1, or vector 1 for the sentence 1, which has a specific fixed size length, and we have a vector 1, and from the sentence 2 that runs through the Siamese BERT model, another pooling layer identical, and it will create a vector B or vector 2. And since we have two vectors in a vector space, we can very easily calculate a cosine similarity. Beautiful. Now, if you want to train this network, because of course the weights have to be trained for our two encoders, two BERT models with each 12 encoder layers, we need a lot of training data sets. So what we have to have? We have a sentence 1, we have a sentence 2, and we have the result, the cosine similarity. So we have to know if sentence 1 and sentence 2 has a cosine similarity of very close, let's say this in words, or not close at all. You can say 0 or 1 or whatever value, however you want to encode it. You also can go with more than two values with a triplet that you say, yes, there is close, it's not close, and somewhere in the middle. You have a lot of options how you can calculate the different classes of similarity. But let's be clear, this here needs a lot of training. The SBERT model has two BERT Siamese networks where you have to do a lot of additional training on a higher level. And our level is now a sentence level. And we compare sentences and we train the system that we say, hey, I know that sentence 1 and sentence 2 has a high cosine similarity. I know that sentence 100 and sentence 101 has a low cosine similarity. And so the system learns on thousands and millions of examples of sentence pairs with a given cosine similarity and adjusts the weights in our BERT accordingly. So we have in SBERT an additional training step on a higher aggregated level, and this level is a sentence. And therefore, it outperforms the normal BERT sentence vector. Let's look at this in detail. Sentence-BERT or SBERT uses as element the pre-trained BERT networks and only fine-tune it to yield useful sentence embeddings. So in SBERT we have the BERT included and already a pre-trained BERT model that has been trained on millions of sentences. So we have a perfect BERT word embedding. And then to fine-tune our SBERT model, we create a Siamese network, or sometimes also called a Bi-Encoder network, because we have two encoders stacked, to update the weights such that the produced sentence embeddings, and this is what SBERT outputs, sentence embeddings, this is so important to remember, that those sentence embeddings are semantically meaningful and can be compared mathematically with a cosine similarity function. Beautiful. So what does it mean, semantic similar? Now, in mathematics, it means that in a computed vector space, those two vectors are close to each other or close by to each other. And here we enter the mathematical area of topology, and it is a non-trivial topic. But let's just say we have two vectors. Those two vectors are almost close to each other. So we know that the semantic content of both vectors are very similar. So what we achieved with this additional training on the sentence 1 and sentence 2 level is we advanced our BERT sentence vector embedding to an additional training step of fine-tuning our SBERT model with this Bi-Encoder structure. So we have another millions and millions and billions of sentences trained if a sentence is similar to another sentence, and we are not just restrict ourselves like the BERT word embedding and the following BERT sentence vector embedding to the pure BERT model. So great. We have this also written down. Here you have the official publication from Sentence-BERT, sentence embeddings using these Siamese BERT networks. And the conclusion on the point 8 is they should say we showed that the BERT out of the box maps sentences to a vector space that is rather unsuitable to be used with common similarity measures like cosine similarity. To overcome this shortcoming, we present Sentence-BERT or SBERT. And SBERT fine-tunes those BERT models in a Siamese network architecture. And therefore now you know why SBERT outperforms BERT in the sentence embedding, because it simply has another training step on the level of sentences. So now you know why SBERT is not the BERT sentence vector. I hope you enjoyed this video, and I'll see you in the next one.